Namaste everyone and welcome to day 10 of our 15-day beginner data science sprint. Over the previous few days, we learned how to load data, clean it, visualize it, explore patterns, and calculate basic statistics. Today, we take an important step forward. We are going to understand how machine learning actually works. We will not begin by training a complicated model. Instead, we will first understand the structure behind almost every supervised machine learning project. By the end of this lesson, you should be able to explain what features are, what a target is, what training data means, what testing data means, why we split a dataset, what a baseline model is, and what data leakage means. Here is today's main question. How can a program learn a relationship instead of being given a fixed rule? Pause for a moment and think about that. In normal programming, we usually give the computer a rule. For example, if a score greater than equal to 40, result equal to pass, else result equal to fail. Here we have manually written the rule. The computer is not learning anything. It is only following the instruction we gave it. Machine learning works differently. Instead of giving the computer a complete fixed rule, we give it examples. The model studies those examples and tries to learn a useful pattern. For example, we may give it information about students, study hours, attendance, previous score, sleep hours, and ask it to learn how these values relate to the student's final score. The model does not understand studying or education like a human being. It only searches for mathematical relationships inside the data. That distinction is very important. Let us first look at the outcome we want to reach today. By the end of the guided demo, we will have four objects. X train, X test, Y train, and Y test. Do not worry if these names look unfamiliar. By the end of this lesson, they will make complete sense. In simple language, X train contains the input information the model can study. Y train contains the correct answers for those training examples. X test contains new input examples that the model did not study. Y test contains the correct answers for those unseen examples. Later, after training a model, we can give it X test, ask it to make predictions, and compare those predictions with Y test. That comparison helps us estimate whether the model learned a general pattern or merely remembered the training rules. Today, we will prepare this structure correctly. This is one of the most important foundations in the entire machine learning workflow. Let us start with simple comparison. Imagine that we want to predict a student's final score. Our approach is to manually create a rule. Predicted score equal to study hours into 10. This rule says that every study hour adds 10 marks. But is this realistic? Probably not. Students with the same study hours may have different attendance levels, previous scores, sleep schedules, and participation levels. A fixed rule may be too simple. In machine learning, we provide many past examples. Each example contains some input values and an observed outcome. The model searches for a relationship between them. For example, So study hours, then attendance, then previous score, then sleep hours and final score. This table is given to us. Or let me show you the image so that you can refer it, understand it easily. The first four columns may help us predict the fifth column. The model studies several rows like these. It tries to identify patterns that help it estimate the final score for a new student. Machine learning is therefore not magic. It is a process of learning a mathematical relationship from examples. Before working with our dataset, let us understand two major types of machine learning. First is supervised learning. So two types of machine learning are there. First is supervised learning. In supervised learning, the dataset contains the correct answer we want the model to learn. For example, predicting a student's final score, predicting a house price, predicting whether a loan will be approved, predicting whether an email is spam. The known answer is called the target or label. Because we already have the correct answers in the historical data, the model can compare its prediction with those answers while learning. Second is unsupervised learning. In unsupervised learning, there is no target column containing a correct answer. The algorithm tries to discover structure in the data. For example, grouping customers with similar behavior, finding similar products, detecting unusual transactions, identifying natural clusters in a dataset. In today's lesson, we are working with supervised learning because we already know the final scores of the students. We want to learn a relationship between student information and the known final score. Before using scikit-learn, we must clearly define the problem. Or before using anything, we must clearly define the problem. A machine learning project should begin with a question. Our question is, can we estimate a student's final score using study hours, attendance, previous score and sleep hours? Notice that this question identifies two things. First, it tells us what information we will use. Second, it tells us what we want to predict. The information used to make a prediction is called the features. The value we want to predict is called the target. So for our problem, the features are these. Study hours, attendance, previous score, sleep hours. And we have one target, that is final score. A simple way to remember this is features go into the model. The target is what comes out. Or even more simply, features are the clues The target is the answer. There is one important question we must ask before selecting any feature. Will this information actually be available when we make the prediction? So this is a very important question. Will this information be available to me when we make the prediction? Suppose we want to predict a student's final score before the final examination. Study hours may be available, attendance may be available, previous score may be available, sleep hours may also be available if we collected that information. But imagine that we include a column called final grade. If final grade was calculated using the student's final score, it would reveal the answer. The model would receive the information that would not genuinely be available at prediction time. This problem is called data leakage. So data leakage is nothing but using some information, using some feature that is not actually available at the prediction time. Example can be student grade while calculating student final score. We will return to data leakage later in the lesson. For now, remember, a feature must not secretly contain the answer. Let us begin the notebook. Our first code cell imports pandas. So the cell returns nothing, but by seeing a tick mark, it tells us that the cell ran successfully. Importing a library usually does not produce visible output. It simply makes the library available in our notebook. Next, let us load the dataset. But before that, we will need to upload it. Again, no visible output appears because we assigned the result to a variable. Let us inspect the first 5 rows. Before running it, predict what you expect to see. We expect to see 5 rows, the column names, and the sample values from the dataset. Now let us run it. At this stage, we are not building a model. We are confirming that the data exists and that the columns we need are present. This is connected to the overall data science workflow. Before modeling, we must understand and validate the data. Let us also check the shape of the dataset. Before we run this, remember that shape gives us two values, number of rows, number of columns. Let us run it. The output is 200, 10, 9. This means the dataset contains 200 rows and 9 columns. It does not mean that every row is correct. It does not mean that every column is useful. It only tells us the size of the table. That is an example of explaining both what an output tells us and what it does not prove. Now we will define the columns that we want to use as features. Before running this cell, what output do you expect? There will probably be no visible output. We are creating a Python list containing the names of 4 columns. Let us run it. We can display the list. The output should be study hours, attendance, previous score, sleep hours. This list makes our code easier to read and modify. Instead of repeatedly typing 4 column names, we store them once. Now we use this list to select the feature columns from the data frame. Notice that we are using a capital X. In machine learning, capital X commonly represents the input features. This is a convention, not a compulsory Python rule. You could not you could use another variable name, but X is widely recognized. Let us run. Now display the first few rows. Before running this cell, predict what you should see. You should see only these 4 columns: study hours, attendance, previous score, sleep hours. Let us run it. The final score should not appear inside X. Why? Because the final score is the answer we want the model to predict. If we include the answer in the input, the model is not solving the real problem. Let us inspect the shape of X. The output is 200, 4. This means X contains 200 student examples and 4 feature columns. Again, this output does not prove that these features are useful. It only confirms the structure of our feature table. Whether these features help the model must be evaluated later. Now we select the target column. A lowercase y commonly represents the target. Again, this is a convention. Let us run. Now inspect the first few values. Before running it, what do you expect? We expect a single column of final scores. Let us run it. Notice the difference. X contains multiple input columns. Y contains one output value for every row. For each student in X, there should be a corresponding final score in Y. Let us confirm the shape. The output is 200, this means Y contains 200 values. The shape looks slightly different from X. X is a two-dimensional table with rows and columns. Y is a one-dimensional pandas series. The most important point is that the number of rows matches. If X has 200 rows, Y should also have 200 answers. Let us print both shapes together. The output may look like this: feature shape 200, 4, target shape 200, In plain language, we have 200 student examples. Each example contains 4 pieces of input information. Each example also has one known final score. This is the basic structure required for supervised learning. Now we reach one of the most important ideas in machine learning. Imagine that a student receives the exact examination questions and answers before the examination. The student memorizes everything. During the examination, the same questions appear. The student scores 100%. Does that prove the student understands the subject? No. It may only prove that the student memorized the answers. The same problem can happen with a machine learning model. If we train a model with every row and then evaluate it using those same rows, the result will look excellent. But the model has already seen those examples. We do not know whether it can perform well on new data. This is why we separate the dataset into a training set and a testing set. The training set is used for learning. The testing set is used for evaluation. A model should not study the test answers during training. The ability to perform well on new unseen examples is called generalization. So let us write it down. Generalization, it is the ability to perform well on new unseen data. So example, you can relate it to with the student exam example. A useful machine learning model should not only remember the training data, it should learn a pattern that continues to work on similar future data. For example, if a model studies data from 160 students, we may evaluate it on 40 other students whose rows were not used during training. This is not a perfect guarantee of future performance. However, it gives us a more realistic estimate than evaluating on the training rows. Scikit-learn provides a function called train test split. Let us import it. Before running the cell, what do you expect? We expect no visible output. The function will simply become available in the notebook. Let us run it. The name tells us that what it does. It takes our data and splits it into training and testing portions. Now let us write the complete split. Do not run it yet. Let us understand every part. We pass x and y into the function. The function keeps the input rows and target values aligned. That means the final score for a particular student remains connected to that student's feature row. Next, we use test size equal to 0.2. This means 20% of the data will go into the test set. The remaining 80% will go into the training set. If we have 200 rows, approximately 160 rows will be used for training and approximately 40 rows will be used for testing. Next, we use random state equal to 42. The function usually shuffles the rows before splitting them. This helps avoid taking only the first 80% for training and the last 20% for testing. But random shuffling may produce a different split each time. Setting random state gives us a reproducible split. This means that when we rerun the notebook with the same data and the same random state, we should receive the same division of rows. The number 42 has no special machine learning power. We could use another fixed integer. The important idea is consistency. Now before running the cell, predict the result. We will see 4 tables printed automatically. Sorry for the interruption. So before running the cell, we need to predict the result. So we will be seeing the 4 tables printed automatically. Is that the case? No. The function returns 4 objects, but we are storing them in variables. Let us run it. The cell runs without displaying anything, but 4 new objects now exist. Let us inspect their shapes. Before running the cell, make a prediction. If the original dataset contains 200 rows and the test size is 20%, what shape do you expect? Think for a moment. We expect approximately x train equal to 160,4, x test equal to 40,4, y train 160 and y test 40. Now let us run it. Your exact row counts depend on the size of your dataset, but the important relationships should remain true. X train and Y train must contain the same number of rows. X test and Y test must also contain the same number of rows. The feature table should still contain 4 columns. Let us explain this output without technical jargon. Suppose we received X train 160,4 and X test 40,4. A plain language explanation should be: we gave the program 160 student examples to learn from and kept 40 separate examples to check how well it works on students it has not seen. That is the most important interpretation. The shapes do not prove that the models will be accurate. They only confirm that the data was divided into separate training and testing groups. Before continuing, explain the most important output in one sentence without using technical jargon. Pause the video and try it yourself. Example can be this. You may say most of the students' records will be used for learning, while a smaller separate group will be used to check the result fairly. If you can explain that clearly, you understand the purpose of the train test split. Let us inspect the first few training rows and their corresponding target values. You may notice that the index values are not in order. For example, you might see indices such as 95, 15, 30, 158, 128. That is normal. The rows were shuffled before being divided. The original index labels were preserved. We could reset the index if required, but it is not necessary for training most scikit-learn models. The important point is that the values in X train will still correspond correctly to the values in Y train. Before training a serious model, we should create a simple reference point. The reference point is called a baseline. So let's write down baseline. It is nothing but a simple reference point to observe model performance. Suppose we are predicting final scores. A very simple baseline could always predict the average final score from the training data. For example, baseline prediction equal to ytrain.mean print baseline prediction. Let us run it. Suppose the result is 50.37. This means our simplest possible strategy is for every student predict 57. That is obviously not a very intelligent personalized prediction. It ignores study hours, attendance, previous score, and sleep hours. But it gives us something to beat. A machine learning model should ideally produce better prediction than this basic strategy. Otherwise, the model may not be adding useful value. A baseline prevents us from being impressed by a result that is not actually better than a simple guess. The average baseline is simple, but it is not always the correct baseline for every problem. For a classification problem, such as predicting loan approval as yes or no, a baseline might predict the most common class. For a regression problem, such as predicting scores or prices, the mean or median may be used as a baseline. Today, we are not evaluating the baseline fully. We are only learning why a simple reference point is necessary. Let us now understand data leakage. Data leakage happens when the model receives information during training that would not genuinely be available when making a real prediction. This can make performance look much better than it truly is. Suppose we want to predict a student's final score. We can use these features. Features equal to study hours, attendance, previous scores, previous score, sleep hours, final grade. But imagine that final grade was assigned using final score. For example, scores above 80 receives grade A, scores above 60 receives B, and so on. In that case, final grade already contains information about the target. The model may appear extremely accurate because we accidentally revealed part of the answer. But in real use, before the final score is known, the final grade would also not be available. That is leakage. Another example would be predicting whether a loan will be approved using a feature called loan dispersed. A loan is generally disbursed only after approval. So that feature reveals what happened after the decision. It would not be available when the approval decision is being predicted. Leakage can also happen in more subtle ways. Suppose we build missing values using the average of the entire dataset before creating the train test split. In that case, information from the test set influences the training preparation. The effect may sometimes be small, but the process is still incorrect. A safer general principle is split the data, learn pre-processing decision using only the training set. Apply those same decision to the test set. We will explore proper pre-processing pipelines in later lessons. For today, remember this question: would this information genuinely be available at the moment when the prediction is made? If the answer is no, the feature may cause leakage. The most common mistake we need to address today is evaluating a model on the same rows used for the training. Imagine that we later write model.fit x comma y and predictions equal model.predict x. The model is trained on x and then evaluated on the same x. This will measure how well the model fits or remembers its training examples. It does not provide a fair estimate of performance on unseen data. The correct structure is close to model.fit x train comma y train and prediction equals model.predict x test. Then the predictions are compared with y test. The model studies the training portion. The model studies the training portion. It is evaluated on the separate testing portion. Remember this sentence: testing on training data measures memory more than generalization. So this is very important question about statement about generalization. This does not mean that checking training performance is always useless. Data scientists often compare training and testing performance to diagnose problems. But test performance must come from unseen data. Here is the complete code we created today. We first load the dataset, then define the prediction problem, then separate the features and target, then inspect them, then create the train test split. Finally, we inspect the result. And after that, we create a simple baseline prediction. At this stage, we have not trained a complex machine learning model. That is intentional. We have correctly defined the prediction problem and prepared separate training and testing data. This step must be understood before model training begins. Now it is time for today's learner challenge. Imagine that you have a loan approval dataset. Your task is to identify three possible features, the target, and one example of data leakage. Pause the video and write your answer. Do not begin with code. First, describe the problem clearly. Here is one possible solution direction. Possible features are applicant income, credit score, existing monthly debt. Possible target is whether the loan is approved. The target might be represented as loan underscore approved with values such as yes, no, or 1, 0. And now possible leakage. Possible leakage is this. Sorry for the interruption. Whether the loan is approved or not. That is a possible target. Possible leakage is a column called as loan disbursement. That is a possible leakage. This column could be a leakage because the loan is usually disbursed after it has been approved. If a disbursement date exists, it strongly suggests that approval already happened. That information would not be available when making the original approval decision. Another leakage example could be approval status message. If that message was generated after the decision, that could be a leakage example. Now, first useful coding step would be to, if the data frame is called loan DF, the first useful step could be writing this code. Your task would then be to create the train test split yourself. Do not worry about training the model yet. Focus on defining the inputs, target, and fair evaluation structure. So let us recap day 10. Today we learned that machine learning uses examples to learn a mathematical relationship. We learned the difference between supervised and unsupervised learning. In supervised learning, the historical dataset includes the correct answers. In unsupervised learning, there is no target answer, and the algorithm searches for structure or groups. We learned that features are the inputs used for the prediction. The target is the value we want to predict. In our student example, the features were study hours, attendance, previous score, sleep hours. The target was final score. We separated these into X, capital X, and Y, small y. We then used train test split to create X train, X test, Y train, Y test. The training data is used to fit the model. The testing data is kept separate so that we can estimate performance on unseen examples. We also learned that a baseline is a simple strategy that gives the model something to beat. Finally, we learned about data leakage. Leakage happens when the model receives information that would not generally be available when making a real prediction. So, what new capability did we gain today? We can now take a clean dataset, define a supervised learning problem, and prepare separate training and testing data. What limitations should we remember? A train test split does not guarantee that a model will perform well in the real world. It only gives us a fairer way to estimate performance than testing on the same data used for training. The quality of the result still depends on the quality of data, the relevance of the features, how representative the test set is, the model, the evaluation metric, and whether leakage or bias exists. Without looking at your notes, answer these 5 questions. Try to explain each answer in everyday language. A good one sentence interpretation of today's output is: we separated the student records into one group for learning and another untouched group for checking whether the learned pattern works on new examples. In the next lesson, we will use this prepared data to train our first learning machine learning model. We will see how a simple model learns the relation between the features and the target. But today's foundation is essential. A model should not be trained before you clearly understand what information it receives, what it is trying to predict, what data it learns from, and what data will be used to test it fairly. That completes day 10 of our 15-day beginner data science sprint. Complete the learner challenge. Write your one sentence interpretation and save your notebook as day 10 how machine learning works. .iping. I will see you in day 11 where we train and evaluate our first machine learning model.